And thanks to all the organizers for giving me the opportunity to talk here today. So I will be talking about the interplay of entanglement and control and quantum dynamics. And the real motivation for this talk is we've been doing quite a lot recently on being able to control quantum dynamics onto a particular manifold of states that we care about. And the motivation came from some measurement-induced phase transition stuff, and actually figuring out how this actually works with the entanglement transition itself. So before I really get into it, let me just acknowledge my collaborators. First, my postdoc, Andrew Alaka, or my recent postdoc, he's at CCNY now, and my grad student, Connor Lemaire, and a postdoc at Rutgers, as well as my colleagues, Shram Ganesh, Jed Pixley, and Tommy Adekola. So first, let's just get into the introduction and motivation. So to introduce things, let's actually just think about the usual measurement-induced phase transition, which I imagine everyone is quite familiar with, but I wanted to highlight a couple of things about it. So first, we're going to have a rate of measurement p. It will go from 0 to 1, and there will be a quantum channel, which will be basically a whole bunch of gates and some one-dimensional geometry with some measurements put in, and we'll often have a unital channel when we first talk about this. So if we put in an infinite temperature density matrix, that's usually what comes out. But one thing that we can do is, instead of looking at the density matrix, we can look at individual trajectories if we actually know the measurement outcomes. And if we normalize by the probability of doing that trajectory, we can get a phase transition and basically the entanglement of the trajectories themselves. So we actually go from a volume law up to some critical measurement rate to an area law. And so this is usually measured with the von Neumann entropy. You trace out part of your subsystem, and you're left with the entanglement of what's left. And if the entanglement scales with the volume of your subsystem, we call it a volume law phase. If it scales with the boundary of your subsystem, that is an area law phase. But we also know that this is not only just a transition for the entanglement. This can actually be seen by putting in a mixed state into the system and asking whether this mixed state either purifies or remains mixed to some finite time that scales with the size of the system. And another way of putting this is that on the volume law side, we can encode some quantum information, at least in an abstract sense. It might be very hard to access. And on the area law side, we lose that information. So to just like focus on this a little bit. So as I said before, this channel is usually unital, and but the trajectories themselves, if we were to put in an infinite temperature density matrix on the purifying phase side, this will actually go to a pure state. And really, I should put some subscript m here. This depends on the measurement record itself. So we get, and one way that I think about this is sort of in this percolation picture. So if I think about this is really going to be a picture with the Hartley entropy, not the true von Neumann entropy. But if I take a ancilla qubit and couple it in, say I couple it into one little qubit down here, I can ask, does this entanglement survive to a late stage in the dynamics? So if I just trace a line through here, I can see that the entanglement can actually spread through these gates, and it can remain entangled with the state through that line. That's not the only way that the entanglement could survive. It could also go this way and be over there. So really, the entanglement, or the entanglement of this ancilla, it's really tracking the purity, but it also spreads out over the system itself. Now, if I wanted to cut this off, I could come in and add a couple of measurements. I add a measurement here and a measurement here. Now, it looks like I might have cut off the entanglement here, but I've actually not because the entanglement can kind of travel back in time. This is kind of why it's a percolation and not a directed percolation phase transition. The entanglement here could actually piggyback on the entanglement that we created earlier to keep the entanglement with the ancilla around a little bit longer. So if I cut that off, then this is when I actually get to the purifying phase. This ancilla now, there's so many measurements around that it can't possibly still be entangled at a late stage. And that is a way that we actually can diagnose whether we're in the pure phase or the mixed phase. And we'll be using the ancilla when we actually diagnose this in our systems. So the thing that we really want to ask, that's sort of the introduction to measurement-induced phase transition, is can we actually control the state of the system using this information that's extracted through the process of measurement? And in a related question, when we have a control transition itself, whenever we actually do control onto a state in some dynamics, can we actually store quantum information in the ergodic phase? So the rough picture, and this is from an actual model, is that there can be this volume law to area law transition. And then after that, when we're extracting information from the phase, we can in principle go from some uncontrolled phase to a controlled phase. And so here in the model, which I'll talk about a little bit more, we can see for some half-cut entropy, the volume law here is that this is increasing with the system size. And then the area law side, it sort of pinches all together quite nicely. And then it really falls off when we get to the control transition and we sort of push entirely onto a state that we care about. So the way that this works is actually quite simple, and it's that I was telling you that these measurement-induced phase transitions very often, not always, they have a unital dynamics. We're going to break that basically by putting in some unitaries after our Krauss operators. So this is like projecting onto the 0 state of a qubit or 1 state of a qubit, and we can now put some unitaries that depend on that outcome. The very simplest thing that you can imagine for spin 1/2 is that you can project onto 1 or 0, and if you measure a 1, you flip the spin. If you measure 0, you leave it alone. Just a simple reset operation. And that will take the infinite temperature density matrix here, which will just be 1, 1. It'll take it to a projector onto 0. And so using this relatively simple idea, us and some others have built this into some of these dynamics to actually control the system in a simple way. So with that, we further took some inspiration from the control of classical chaos. So let me describe this a bit. So you'll kind of see how this is related to what we're doing with the measurement-induced phase transition. So this kind of comes from a field called the stochastic control of chaos. And a view from the top here is we have some mixed phase space. This is all classical right now. Mixed phase space with some periodic orbits that are stable and some that are unstable. And if we take the system, we can look at here that we have some stable orbits, and right at the edge of this, we have like the last stable orbit, or the one that first becomes unstable. And we want to ask, so we have, if we have, so first, if we have like small changes to the initial state or model parameters of the system will be chaotic. You're sort of kicked all over this ergodic region. And the thing that we want to ask is there a systematic way to stabilize these unstable orbits, or even convert them into a global attractor? That'll be controlling onto the manifold of states that we actually care about. And so this has been achieved classically, and this is I think this is the first paper on this. So the idea is that we randomly intervene in the dynamics. So you have some ergodic dynamics that are kicking you around your phase space. And then with a probability, 1 minus p, the chaotic map will be allowed to proceed. It'll keep kicking you around the phase space, making things quite ergodic. Then with a probability p, we'll come in with a control map. And what the control map will do is it'll measure the system's location. This is quite trivial in the classical sense. You just sort of look and see where it is. And then you push the state a little bit towards the orbit that you care about. And so that's the feedback that way. So we measure, compute how far we are, and do some feedback onto the system. So as a function of this probability P, you actually get a controllability phase transition, even classically, where the unstable orbit actually becomes a global attractor in the system itself. So that's classically. Now, when we marry this with the measurement-induced phase transition, we can start to ask how these play with each other. And so now I want to basically give you a big overview of what we've learned from both from this research. So the big takeaways. First, if we introduce feedback into these hybrid quantum dynamics, we can control the system onto a target manifold or even a trajectory of the dynamics that is inherently unstable. So this will lead to a control or absorbing state phase transition. And the universality of this, we found there's two main universalities that pop up over and over again. One is a random walk universality and also directed percolation. And also, if we start to do something long range, we can start to tune this universality away from this, and we can get different critical exponents that vary based on how long range our system is. And then some of the major points that we've actually learned here is, first, the entanglement transition, either viewed as a purification or volume law to area law transition, it is kind of generically seems to occur before the control transition with its own distinct universality. In fact, the universality will usually be what has been seen for the measurement-induced phase transition before you put any control in. And on top of that, whenever we put either long-range updates or we make the Hilbert space on site quite large, we can actually merge these two transitions together. And when we do, the control transition's universality will be what actually wins in the dynamics itself. So with that as the big takeaways, let's now talk about two specific models where we see this. So the one I'll spend the most time on, and if there's time, I'll do the second model, is what we call the Bernoulli circuit. So here, this will be a picture, kind of a cartoon version of what actually is going to be occurring eventually in the quantum circuit. But let's actually build up how we get to this here. But once we have this, we'll be able to do a lot of things. We can do a random automaton circuit. We'll be able to do a random quantum circuit, build StatMech model, and even put it on an IBM quantum computer. So first, this is actually inspired by something called the Bernoulli map. And it's kind of the simplest chaotic map you can imagine. It is basically you have a real number, you multiply it by 2, and you mod it by 1. This basically takes the interval 0 to 1, and it folds this blue region on top of this red region. And this simple operation is actually just chaotic. And it's chaotic basically because there's a whole bunch of irrational numbers on the number line. And if we take, say, a number like 1 over square root of 2, then if we run the dynamics, it sort of fills up this number line eventually. On the other hand, rational numbers, they will actually live on unstable periodic orbits. And so, for instance, if we just take 1/3, this period 2 orbit, it'll just go back and forth between 1/3 and 2/3 forever. And that'll be a period 2 orbit, which we'll see later will be one example of where we can control. The control map, at least in its very simplest form, will be to actually control onto the simplest periodic orbit you can imagine, which is just 0. So 0 gets mapped to 0 gets mapped to 0. And this will basically just be you take the real number and you multiply it by some real number less than 1. This takes the interval and just scrunches it up. So when you do this, you have a probability of doing the Bernoulli map and a probability of doing the control map, and also how much you scrunch up the interval. You can get an analytic result for where the phase boundary is. It looks something like this, and you'll get two regions: one where you're uncontrolled, and one where you're controlled. And when you're controlled, you're basically being pushed entirely to the orbit that you care about. In this case, the orbit is just 0. So to map this to qubits, we basically take this real number and we write it as a bit string. And if we take this bit string, we can then just map it onto quantum bits. So we have both the most significant and the least significant bit all the way to the right. And then the operation of multiplying 2 and modding by 1 will just be the same as shifting all of your bits over. So but we'll actually need to truncate this at some point. So we'll actually have a bit string that will be truncated at order L. And this will introduce an error in the system that's 2 to the minus L. And when we do this, we can implement this by basically just doing a translation operator, where we take all the bits and we just move them over, and we take the first one and stick it on to the end. So this, and this will, and we'll be targeting this fixed point here. But the problem with this operation is you can kind of already see with the way that it's drawn here, it's kind of a trivial operation. It's just relabeling your qubits. Nothing is really happening. And in fact, this is like encoded factors. We've actually deleted all the chaos from this model by doing this. It's no longer even ergodic in any sense. So in order to actually recover chaos, we have to add back in what we call a scrambler operation, which takes the last digits, digits in your bit string and just scrambles them up. And this is where we can actually start to put in entanglement into the system as well. So here we can put a 2-qubit gate or a 2-bit permutation matrix, whatever you like, if you want to keep it classical or if you want to make it quantum. This S here will basically do this for us, and your intuition for this should actually come from the fact that we've actually, by truncating this, we've made all of our numbers into rational numbers, right? But if this were a truly irrational number and you shifted it over, you would have no idea what your next bit would be. It'd be like equally probable to be either 0 or 1. And so our scrambler is really simulating the irrationalness of the next of the number that is not on a periodic orbit. And these are actually called normal numbers. They're dense on the real line. So great. We are now mapping this operation of the Bernoulli map onto this circuit where we not only shift, but we scramble. Now, the next thing is just the control operation where we scrunch everything down. And this will just be basically shift everything to the right and reset the first qubit here to 0, which can be accomplished by measuring it and doing feedback if it's a 1. And so that we represent here by first resetting this will actually reset the nth qubit, and then we inverse translate, moving everything back. So this operation, though, you should note that the areas aren't preserved in this phase space, so this will be inherently non-unitary, which is why we actually have to do this measurement procedure. So if we stochastically combine both the Bernoulli operation, the chaotic map here, and this control operation, then we can, as well as unwind all of these translation operators, because we can always just keep track of classically which bit we mean by this labeling scheme. This actually unwinds into entirely what we have on the right, where these 2-qubit gates represent what's left of the Bernoulli map, and these blue things are basically just the reset operations. So this circuit ends up just being a biased random walk, and the bias will be determined by P. If it's P, it's biased into the random walk where we have a whole bunch of scrambling. and if it's biased above 0.5, it'll be doing more resets than scrambling, pushing us onto the all zero state. So mixing these together, we can actually just compute what the phase diagram is. So this is with some stabilizer dynamics. Our scrambler will just be a Clifford gate. And in this case, we actually get exactly this phase diagram here. And if we look at the entanglement phase transition, we can actually see that the half cut it grows like the log of L, and even the time dynamics grow like the log of the time, just completely consistent with what we know from the regular measurement-induced phase transition. And we can even compare all of our universal exponents. So here, I want to highlight this is the measurement-induced phase transition that we find, and this is the one from the literature. And there's quite good agreement, not with the non-universal stuff like PC, but the universal exponents seem to match quite well, with maybe some slight discrepancy and some with a couple of things, but that could just be numerical error. On top of that, we can move over and look at this control transition, and this one's quite nice because we can just look at a single observable, the magnetization. The all zero state is a one magnetization state. And when we do this, we can see that this magnetization has a very nice crossing, indicating the phase transition that happens exactly at 0.5. And if we look at even the half-cut entanglement, we can start to pull out even the dynamical exponent that we'd expect for a random walk, which is z equals 2. And so pulling all that out, we can get very, very good accuracy on the control transition. And all of these can actually be analytically found as well, and they agree quite well. So that's sort of generically what seems to happen. But one thing that we can do now, this is actually targeting a very simple state, right? So the all zero state. What happens if we try to actually control into a more interesting state? So we can actually go to this with actually the period 2 orbits. So where we actually go to the 1/3 and 2/3 orbit of this Bernoulli model. And there are two ways in which we can actually target this. One way is with local resetting. And so before we had something like this. You measure Z and you feed back and you do an X depending on that outcome. This will target the all zero state. But now we can actually do a parity measurement on 2 qubits, and based on that outcome, if it's both 2 1s or 0 0, we can then flip one of them to put us back onto something that actually targets these 2 nil states. And it turns out these 2 nil states are exactly 1/3 and 2/3. So if we do that, we've changed our what we can control onto. It turns out that if we look at, say, the this is the ancilla entropy, that we get very similar universal exponents. It's just that the PC value has now moved up to about 0.37 in this case. But the main takeaway is that the critical point, it moves, but the universality remains unchanged. So even though we're controlling onto a different state, it doesn't, the measurement-induced phase transition doesn't care. And also the control transition doesn't care. It still occurs at the same point with the same universality. But now there's a different way we can target these 2 states. It's actually the way that we first did this problem. And that's by actually doing the same little local reset, but then doing a controlled adder across the entire system. And so I won't go to the details of how this targets these states. You just have to trust me that this big global adder will actually push you towards one of these 2 states. And so you actually get this periodic orbit. And when we do this, something quite different happens. And that's that we get this volume law entanglement across all p values before the control transition. And if we look at how the entanglement changes at the control transition, it seems to be inheriting the critical values of the control transition. And so the big takeaway here is that the entanglement transition is pushed towards the control transition when we have this global operation. And as a result, it actually inherits the the universality of that transition. So we actually get PC around 0.5, and we get all these critical exponents that you would normally get for the entanglement values. So that's one way that you can push these two transitions together. Another way is actually by going from qubits to qdits. And so when we turn into qdits, we can push these two together. And the way you should think about this is we modify the Bernoulli map now. So instead of being 2x mod 1, we do dx mod 1. And d is equal to 2 is qubit. Arbitrary d is just an arbitrary qdit. Our control map will also be x divided by d. And in order to really separate things out and to understand what's going on, we not only have a probability of control, we start doing a probability of just having random measurements in the system too. When we do this, the quantum analog will just be this 1D qdit array. And we can actually take the d going to infinity limit as usual to get our Potts model. And this will actually just be a Potts model on a random graph. And that can be exactly simulated, and we get this phase diagram. So q is equal to 0 is what you'd expect without any of these random measurements. And the volume law persists all the way up to the control transition. But if we start to put in our random measurements, we can peel away the measurement-induced phase transition. And we actually we recover the percolation universality, which will then be suppressed as we get close to the control transition. So just a summary for the Bernoulli circuit, what we've learned here is that we have a control transition that occurs at 0.5 pretty much all the time for our values. And the entanglement transition kind of generically occurs before the control transition. When we have local feedback or a finite on-site dimension, it's strictly less than the control transition. And it usually has its own distinct universality. If we have global feedback, we can push it towards it, and the measurement-induced phase transition will actually merge with control, inheriting its universality. And if we let the on-site dimension go to infinity, we can again merge these transitions. But it seems like most of the time, the control transition just will swamp out the universality of the entanglement transition itself. Okay. So I don't have a whole lot of time, so I'm just going to flash the main points of Model 2 without going into much of the detail. Model 2 is actually like now doing a chaotic PXP model where we have some chaos and some control, but the key thing about this model that I want to highlight, and you can ask me more if you want during a break or something, is that we do collective measurements where we measure some collective magnetization on either the even or the odd sublattices, and we then do our feedback based on the outcome of that measurement. And so we have some chaotic dynamics, the control dynamics, and we have an orbit that will actually target. It's an orbit from all zeros to both nil states. And let me just get to skip through most of this. This is quite nice because you can do these nice orbits that Tom was able to simulate quite nicely. And if we look at the control transition, which we can define an order parameter for, you actually find, and this is quite nice because you can compare with the classical result to quite large system size. It's just an automaton circuit in this case. We can find some universality here that seems to be a second order phase transition with a z which is less than 1, a dynamic exponent that's less than 1. So like things are changing quite more than a light cone in this system because of the global operation that we're actually doing. And in the quantum limit, it's actually quite consistent. We can do the order parameter. It agrees very broadly with what we see in the classical case. And for the ancilla entropy, we can get very similar dynamical exponents. And the big picture is this. So here, the probability of doing the control operation is P. Probability of doing these little purple like corrections is Q. And we can actually find a phase transition between the uncontrolled and the controlled side of these dynamics, and we get critical exponents which actually change continuously. Some dynamic exponent z, which goes from somewhere around 1 to around 0.6, and a correlation linked exponent which changes with the inverse of that. And the big takeaway here is that these are occurring. This ancilla purification transition and this order parameter transition are occurring quite close to each other, and they seem to have very similar universality. And so the big takeaway is that these collective measurements we're doing of the magnetization, they've sped up the criticality, where z is less than 1. And the same criticality appears to happen for both the entanglement and for the control transition itself. And so I'll just end with my conclusions here, that we see that with these hybrid quantum dynamics, when we put control onto the system, that we do indeed get control or absorbing state phase transition with very generically random walk or directed percolation. And with the collective measurements, we can get a more tunable universality. And we can push these two transitions together with long-range updates, which can either be in the form of a unitary, like with the adder that we did in the first case, or with these collective measurements, which actually are also kind of a global update to the system. Both of these seem to push the transitions towards each other. With that, I will end there. Thank you.
Questions?
Thanks for the very nice talk. I just want to clarify, I think you mentioned, are these all considering Clifford circuits or not really? And what happens if you change the dynamics to? Yeah,
well, the first plot I showed was on some Clifford circuits, but we originally did this with Har random up to like 2024 sites, and you see very similar stuff. This seems to not really depend at least the control stuff doesn't depend too much on whether you're Har or Clifford or even permutation circuits. But the entanglement transition universality will change depending on what you do there.
Yes, maybe for the control transition, like, do you expect the universality class to like depend on like what you measure and what you control? Like, does it depend on the details of the form, or like not really?
So
exponents.
Yeah, with it depends on the dynamics a bit. So like usually with these local changes, we've seen this random walk in this or a directed percolation. I didn't show any directed percolation stuff here, but as far as like that changing depending on, I guess if that can change depending on whether it's stabilizers or
like what if you are not measuring parity? What if you're measuring like some?
So the magnetization measurement, for instance, can't be done with Clifford. I don't think. You have to do some dispersive readout or some other quantum phase estimation, which would break.
Yeah, sorry. Clifford. The question is, what happens if you do if you do something beyond the stabilizer or like more general operator, and then you do this?
So I think that it depends on what specifically we're talking about. But for a lot of the control transitions I was mentioning here, it doesn't depend so much on those details, at least for the control.
A control transition, a lot of people are interested in this quantum error correction. I don't know if you wanted to, like, is there an analogy that? Yeah, no,
I think that there's potential for analogy with quantum error correction, both like from the control side itself, whether you want to control onto like a relevant state to like actually do some encoding, or whether you want to actually encode something in the ergodic side of the phase itself.
Hi, thanks for the exciting talk. So the control transitions are features of the channel that you're applying, and so they're intrinsic, yes. But the entanglement or other transitions in the trajectories are obviously a function of the unraveling that you choose, and the unravelings you're choosing obviously are physically motivated, like measure and flip, but yes. One could ask about more general unravelings for the channel, for example, weak measurements instead of stochastic, strong measurements, and so on. That could move the MIPT critical point, right? So yes. A question that's pretty natural is if you could push it all the way up to the control transition by choosing some very, clever, maybe non-local unraveling. But have you played with that at all?
Yeah. So like we played with some things maybe slightly related to this. I don't think we've done like weak measurements, but I don't expect it to actually change that much. I expect it to maybe move where the MIPT actually occurs, but it seems really hard to push the controlled transition to, or the MIPT to the controlled transition using stuff that's only local, even if you like weaken your measurements or things like that. It really seems to be you have to do something global to the system to really make them like the same. Right.
One more small question. How entangling is the global adder that you are using in the second?
Oh yeah, that's a very good question. It really depends on obviously if you give the adder a just a bit string, it doesn't add any entanglement, right? But it can be. Oh God, we looked at this very carefully years ago. It adds a bit of entanglement, but I think the main thing is that it can help to move entanglement that's already there across the system more than it does also add a bit of its own depending on the state.
Thanks.
Hi, thank you for this nice talk. My question may be also relevant to the second question about the relevance to quantum error correction. Because if I am thinking about in the context of quantum error correction, the control transition sounds like you do some real-time feed-forward conditioned on your error syndrome, extracted error syndrome. So I just wonder if there's some mapping between this setting and the quantum error correction, and if so, how should I understand these non-range updates are needed? Because normally we just hope to do some local update.
Yeah.
Based on quantum error syndromes, yes.
Yeah. So I think one way of potentially thinking about this is in maybe the context of the toric code where you where you entangle a qubit into the system, and there's a question of you have a quantum channel that you can do error correction on, and then but if you were to take your quantum channel and unravel it in two different ways, whether it's with some unitaries or some measurement, is there a measurement-induced phase transition that occurs on the measurement side? There obviously isn't if you unravel it with unitaries, right? Mm-hmm. And so in principle, your qubit information is there. The channel might have lost it though because you can't do quantum error correction there. That would be that would be the region in between for us, the volume law and the controlled side. That would be information may be still there but super scrambled up. Mm-hmm. Whereas if you're able to lose it entirely and have this you lose the information and it's scrambled up, then well, you can't do anything.
I see. Yeah, thank you.
All right, thanks again for the talk. I was wondering if you could tell us a little bit more about the collapse of the control transition and the measurement-induced phase transition as a function of the on-site helper space dimension. Do you think that's kind of a universal feature? Was it particular to your model? Because I could kind of imagine if you increase your on-site helper space dimension, you have more knobs to tune. So your control transition, it becomes a bit stronger. Yeah. But I was wondering if you could say, is there some reason that it should be they should universally collapse as you increase that on-site helper space dimension?
So my I'll just be speculating here because we haven't tested it in full detail. But I do think that this probably does depend on the model a bit. And so I actually but it was actually surprising to me that this was not doing this like initially. We actually even spent a fair bit of time looking really closely here to see if they were actually different from each other, but you get numerical noise and stuff at this case. So I think the simple answer to your question is I don't think that it's a universal thing that as you increase D, that these will merge together. But I think it's kind of what you were saying. There's a lot more to play with just on site, where you can kind of keep your entanglement because there's just a whole lot of extra degrees of freedom on the site to that allows you to at least push them together, if not to merge them.
Thanks.
Yeah.
So I guess going back to the Bernoulli map, where you showed this 2 periodic orbit.
Oh yeah.
Did I understand correctly that you're kind of kicking the system back and forth between 2 product states?
Actually, this depends on how you do it. You can actually do it both ways. So actually, in the initial way that we did it with the global adder, it actually does kick you between 2 product states, so it's entirely disentangled. But if you do it in this way, this actually doesn't care. It treats both of them the same. So if there's any coherence between these 2 states initially, that coherence will change a bit as you do this non-unitary dynamics, but you can maintain coherence between the 2 nil states there. And so actually the local updates, at least in this case, can give a more interesting controlled state at the end.
Justin, quick question. Do I understand correctly that all the scaling exponents of the underlying classical model translate verbatim to the quantum model, or are there surprises, when you...
Yeah. Well, so I guess, yeah, it really does seem to be that all the classical exponents just seem to carry over just entirely to the quantum thing. They even see it really feels like when you're messing with these models that classical physics just like wants to overwhelm your quantum mechanics. Like you can even see here, like this is the half-cut entanglement entropy, and this seems to happen at least in the Bernoulli circuit no matter what. That you get very nice collapse with a T over L squared with a square root. So this seems to be behaving, even the entanglement itself seems to be behaving diffusively like you would expect from a random walker, which is kind of what this is showing.
Thank you.
Okay, great, perfect time. So now we have a break until the morning session resumes at 11, I believe.